I'll take you up on that later then. Good morning, everyone. Please, if you have questions or comments during my presentations, please fire them off. It gets much more interactive. I do not get too bored. Probably you will not either. So please do. Can we agree to this? Yeah. Thank you.
There's no problem. You may regret it. But
Then I can learn something as well. Okay, let's give it a try then. Who's here to lock their HW12 to the GPS? One, okay. I probably failed the audience then. But maybe you can use it for something else than say just your old Heath kit. It could be WFO, signal generator, whisper transmitter, 10 megahertz reference, or a 13 megahertz reference if that's what you're looking for. Those are just some of the applications that you can use. I'm sure that some of you may even dream up new applications or new programs or new functionality that has not been used before. So if you have that in mind, please ask questions again, comment on it. Today is not a deep technical discussion as such. It's more to give you an inspiration of what you can do this coming winter. For yourself or for your clubs, for instance, so that you'll be ready for spring and can go portable if that's what you like to do with your HW12. First question, which ones of these ones do you prefer? I've got two spectrums here. Which one prefer the first one over here?
depends what you're doing.
We'll get back to that. Okay, which one, who prefers this one? 2 versus 20. Interesting. Why do you like this one? You don't like harmonics, do you? No. But you seem to like in-band spurious, right? Compared to this one, at least. To get rid of those, just put a low-pass filter on it. That's doable. But to get rid of in-band spurious, that's much more tricky. That will require a crystal filter, if at all possible. I think you will find some messages in my presentation then. Thank you. So what's on the menu? Well, basically it's Arduino. Some of you may be aware of Arduino before. How many have used an Arduino? Thank you. Writing your own code for the Arduino? Great. Who's familiar with the SI chip? Yeah, about a third, maybe half. GPS, you're probably all using. And if you don't, you probably didn't find it here anyway. So, yeah. So we got the Arduino, there's the SI chip, a GPS receiver, and then there's a green board down here. I'll get back to that at the end of the presentation. Why Arduino? I'm pretty sure some of you like to stay on your Picaxe or Raspberry Pi or your old 16F84 if that's what you prefer. Yeah, you know it inside out, but maybe it's time to upgrade. These are just some numbers. If you Google Arduino, you'll get about 91.6 million hits versus below a million and 60 million for Raspberry Pi. eBay, you can also see the numbers, 250,000 hits if you type in Arduino. That being said, a lot of the hits will also cover smaller PCB or circuits that you can use for all the other platforms as well. But this is just to give you an idea, and I'm not saying to close the discussion whether there should be Arduino or something else. In my mind, Arduino is the greatest invention since sliced bread, and definitely for radio amateurs. It is. And you can get Arduinos from eBay for £2, £3 delivered. It doesn't even pay off to build it yourself or assemble it yourself, really. Then the transition, if you used one of the other ones, may be a little hard in the beginning, but it's definitely worthwhile. And the community, as you can see here, M is members in the forums and P are posts. So there are a lot of members definitely in these two ones. And there's always somebody else who've done it before. Sorry to say, but that's always the case. Or at least parts of it, so you can carve out the functionality that you're looking for, and then sort of swing it around, implement it in your own application. So these are some of the reasons why I think Arduino is a great tool to use. What is Arduino? At least for those of you who don't know it, it was created by some Italians. That doesn't make it any bad. It's a brilliant tool. It definitely is. It's open hardware, open software, which is probably also one of the reasons why you find a lot of Chinese people cloning it. And that's the reason why, because if you buy an Arduino from the Arduino themselves, it's probably 10 times more. Or if you buy it in the local street, if it's a genuine Arduino. And you can get processors from 8 bits running at 60 megahertz up to 32 bits ARM processors at 84 megahertz. For very many radio applications, that's more than required. Some will then say, okay, but the Raspberry Pi goes close to 1 gigahertz. Yeah, but it has an operating system. There's a lot of, say, other stuff that has to be maintained. With the Arduino, you can more sort of cut to the chase and do exactly what you want, and you don't have to look into understanding the operating system underneath. Another advantage is that you don't have to read, unless you really want to, the data sheet of the microcontroller itself. That's the chip that you see up here. You don't have to understand it, really. Arduino offers you a lot of abstraction to it. You just say, okay, I want something on port A3, and the system will then figure out what to do about it. And the beauty is, even if you find code written for an Arduino Uno, you can use the very same on the Nano. The ports are named in the very same way. At least right now. If you go into more advanced details and so forth, and you get closer to the microcontroller itself, you have to be much more aware of the details. But for a beginner's point of view, for the club to get started and so forth, don't even think about reading the datasheet. You don't have to. And programming it, it's really easy. I'm sure everybody's comfortable with using a USB port, unless Windows hicks up or whatever. Then there is the transition, as I mentioned before. It's C, C++, sort of an Arduino dialect. Of course, if you've used assembler or BASIC or Pascal, I came from the Pascal world at college, but never really used it since. So I started writing C in 2011, hadn't really done any C before except kind of reading other people's code. To a very large extent, you can convert it line by line if you really have to. But again, the community is so large, so there's always somebody who has done it before. Just pick their code and you're free to do it. And there are really many YouTube videos available. So don't be afraid, try it out. The Hello World equivalent in the Arduino world, that's a blink program that blinks an onboard LED. So, and you can download a small sketch, as it's called in Arduino, a small program that will get the LED flashing. And that will at least give you some idea whether you have done it correctly or not. So the SI chip, I'm glad that so many of you have some experience with it. It goes from just above 2 kilohertz to, in the specification, up to 200 megahertz, but you can definitely get higher. But it's beyond the specification. I have tried 300 megahertz, that doesn't work. 280 works, but it probably is chip dependent. So whether it will work or not, that's a different issue, but you can always try it out. Whether there will be any permanent damage to it, I don't think so. It has 3 outputs. You can see the schematic here, 1, 2, and 3, or 0, 1, and 2. And you can use it for sort of various things, and we'll get back to that later on. For instance, IQ quadrature modulation, if that's what you're looking for your SDR. Then you can build yourself a cheap little VFO. It needs a crystal that you can attach here, 25 megahertz or 27, and the performance of the crystal is reflected through the entire chip up onto the sort of end-used frequency. And even the load matching and so forth is built in. So it's more or less a self-contained chip. It doesn't require a lot of external components as such. 10 milliwatt output. Frequency stability, as I said before, it varies a lot with the performance of the crystal. If you have a 100 ppm, you'll get a 100 ppm performance all the way, of course. Otherwise, if you get down to 10 ppm, then it's a different story.
What about far-out phase noise?
Phase noise is pretty good for the price, yeah. I can't recall the numbers, but again, it's also the crystal to some extent, and then you got the
Far-out phase noise.
I don't have the numbers, but on top of my
By next week.
yeah, yeah, we tried to multiply 1 to 10 gigahertz, and it's okay for the purpose and the price, of course. You have to take that into account. It's not as good as an oven-controlled oscillator, of course, 10 megahertz, but for the price, it's fair.
How does it compare with one of the proper well-known synthesizers, the ADS?
In a one-to-one comparison, don't know. I don't have much experience with those. I just make the code for some of them, and then okay, boring, next chip. So, but it would be a good article for Ratcom, definitely. Yeah, it is. Yeah, and there are many breakout boards. That's say small boards that you can buy from various shops around the world. They are typically around $10 or so. They are, at least the one I have, I've got this one from Adafruit. I think it has 100 ppm crystal on it. The printed circuit board layout is not really sort of RF proof as such, which is one of the drawbacks that very many people who do this see it from a digital way of thinking, and it is a digital chip, and it's very good for a digital domain, but digital people usually don't care much about spurious. They care about phase noise or jitter in the time domain. So if they can have minus 20 dBc spurious, that's fine with them. But we're radio amateurs, we know better, don't we? Silence. The thing about if you got something on the side, well, as Andy said, phase noise or so, it will affect both your transmission, but also reception, that you will hear stations that you're not intended to or you do not plan to hear. So it is important with the sort of off frequency signals. Now this is the math inside the SI chip, and also the functional block diagram. You have the crystal here. It can be 27, 25, probably also in between. There is a Russian amateur who has tried sort of various input frequencies with limited success, I would say. There is a phase comparator which compares the phase of the output signal with the crystal, and when they are in line, it's on frequency. We won't go into details about this because, again, this is about sort of inspiration. But by the end of the day, you'll get down to a formula that looks like this. And for those of you who are still comfortable in your math, it's one equation with 7 variables. We can't really solve that. I'm sorry. So you can go home now.
Using the GPS.
Yeah, that's one of the drawbacks. It's somewhat complicated, but if you're really into math, it's not that difficult. There are some limitations on A. I think it goes from 15 to 90, I think it is. It's not really that important right now. The hint here is, if you set E to 0, then F becomes irrelevant, but you could put it at 1, then you only have the D part left. And if you put R or equals R to 1, then you simplify this formula. And then the way it works is that you take your output frequency, the F out here, and then you sort of work your way backwards. At the end of my presentation, I have a link to a page that goes much more into details about this. And the beauty is, if you do it right, you can get an accuracy to 1 millihertz, but you have to do it right. If you do it the most common way that I've seen, Googling and so forth, you can't get it that accurate. And the trick is, the match between B and C, or E and F, but E and F can be excluded. And for all the application I've seen, it's not relevant to have what is called a fractional ratio out here. You can easily live with an integer. The fractional ratio you can work with here, and that's a much better way to do it performance-wise in the RF domain. So don't try to, because you don't have to. 1 millihertz is pretty good for most of us here, I'm sure. And if you can live with 10 millihertz, you can do a slightly faster calculation, but we're really down to virtually nothing, even in an Arduino. So again, if somebody's saying to you, well, you shouldn't go into details, it's not really that difficult, to be honest. And again, I'll give you a link later on for a website. Fortunately, it's not been running. I'll get back to that later, but it will be. This is some part of the code. You don't have to take notes of this, of course, because you can do it later. But this is just to give you an overview. In the data sheet, it's over here. It says exactly how you should initialize the chip, and you just go down step by step. Again, I've seen other implementations. They may have various reasons for doing it. Some of this is not entirely logic to me either. I like to close things down and then set them up before I fire them up eventually. To some extent they say you shouldn't do it like that. Okay, it sounds a bit backwards to me, but okay, I'll stick with the datasheet flowchart. Do that, save yourself some time. But this is kind of the initial flow in an Arduino program. For instance, here it says write the value, the hex value AC to register 177, and this is how you do it. It's not that complicated, right? So don't be afraid that that this might involve some software writing that you have never ever done before. Again, give it a try. Nobody will improve if you don't try, that's for sure. Nobody gets better riding a bike without trying to ride a bike. So, this is, well, this is what I really want to talk about. The rest is just Arduino stuff. But this is really no good. These are some pictures made by Karen, K3ARW, I think his call is. APW, sorry. Says down here. Well, also in the URL. He has made several measurements. And as you can see here, these are 10 megahertz bands. And you have the sort of intended carry up here. And you have what is about 50 dB suppression of the spurious here. This one is only 45, roughly speaking. This is why you should be very careful. And one of the reasons why, if you use sort of off-the-shelf boards, probably even some of the radioamateur applications available, I'm not sure how much detail they pay to this. And it would be pity spending a whole winter building something, and then by sort of just taking not a detour, but a different route initially, you could have done 20 dB better. So please keep this in mind. Keep this in mind. And I think a lot of people who use the SI chip are, say, in the HF domain, not the VHF, where I'm mostly operating. But with increasing frequency also comes sort of worsened performance. So can you use the SI on 2 meter? It depends. Even with sort of a proper layout and so forth of the PCB and the circuit around it, it depends. You shouldn't amplify it too much, is my advice. It's possible, and I'm sure there are people using it there, and they're perfectly happy. There is Beacon in California. They use it on 70 centimeters. They're tripling the output signal. But they have a huge filtering afterwards. So please keep this in mind. One of the funny thing about it, it's a square wave that comes out. And you can actually take the harmonics and use them. So you can, if you are looking for a 70 centimeter generator, signal generator, for lab use, you can use it for that, even on 23. You just take out the ninth harmonic. That's possible. And then you have a cheap little, or poor man's signal generator. So, so that's possible. Now, these are some general design tricks or tips that any radio amateur should apply when doing something on his own or at the club. Most people probably subscribe to the first ones, keep the RF and the digital circuits apart, short wires, digital should not, the tracks should not be too close together and so forth. The next one, voltage regulators or power supply. Too many, I believe, saying, oh, I can save a voltage regulator for less than £1 if I use one for all. But maybe that's not a good idea. So much rather put on another voltage regulator to get some isolation between the various circuit parts. And definitely between the RF domain and the digital domain. Because the digital domain will most likely sort of make noise into the RF circuit. And you need all the isolation you can get. Also through the power supply. And those who are using a phone charger, please stop doing it. Your neighbors will not appreciate it. Well, your fellow radio amateur neighbors will not appreciate it. And again, from a reception point of view, if you're using it as a VFO, you will be subject to unwanted signals yourself. So there's really no good point in using it, except it's just available right now. And some who even use the USB port, that's even worse in most cases, to power up your entire circuit. It's good for development, but once you want to put it on air and you apply some power to it, 5 watts, 10 watts, or even more, you should really be careful about the spectrum. Decoupling, that's also a standard thing by radio amateurs, but inline damping resistors, that can be in the I2C chain or protocol or path, sorry, that you put in some 100 ohm resistors in case there's some reflected energy back and forth. Because this is just like an antenna. Even it's a digital circuit, there will be reflected currents going back and forth. And if they are not sort of terminated properly in the receiving device, they will be transmitted back or reflected back to the microcontroller. That again may start to misbehave and make noise all over the place. If you can, go for SMD components. I know it might be tricky for most people, but it's really worthwhile. And these days you can get online PCBs at a reasonable cost from China, and if you want to take it a bit further, you can buy stencils to apply solder paste, and that will give you a really, really neat look afterwards. And much better reliability. Now, multi-layer PCBs. I'm not sure how many are comfortable with doing that, but it's not more difficult than using or designing a standard 1-layer or 2-layer PCB. And the trick is to have the RF sort of domain at the top of the circuit or the PCB, and then at the very bottom you have the digital layer. So whenever you're at the top of and you have the microcontroller, you put a via, go down to the bottom layer, and then you route down there. Second layer, that's the ground layer, and then third layer is the voltage layer. That's a very good way to separate things. It does have the impact on price if you order it, and probably not very many can make 4-layer PCBs themselves. Of course, you can glue 2 standard FR4 PCBs together, but you'll probably get a 3-layer PCB, which is not bad as such, but you can get say half Euro card size PCBs for around $5 online. If you go up to a 4-layer, the price will increase tenfold. But again, if you're spent 2 months all winter, I'm sure you can sort of afford the additional cost, because it will give you much better performance. And then this is just a comparison. This is a digital circuit from a professional signal generator. You don't have to have a sort of cast aluminium enclosure or have sort of the local skilled guy in mechanics to drill out an enclosure for you.
But if you buy junk from junk sales,
then you can probably scrap it, yeah.
Then you get a lot of those.
That's true.
You just have to make your boards fit them.
Yeah. That's true, but it's possible, definitely. Now, one of the things you can do, you can build yourself a frequency counter. In the microcontroller world, it's not really that difficult, and you can do it with a sort of standard off-the-shelf Arduino Nano for less than £3. You can build yourself a close to 7 megahertz frequency counter. So if you're just active on 40 meters or below, then you can build yourself a really cheap frequency counter for your HW12. But if you want to go a bit higher, then you have to use different tricks, either a faster microcontroller that can sample faster, or some of them even have sort of a built-in circuit that can run beyond their clock frequency. And there are some reasons why and so forth. If you want to go much more into that, that's the Nyquist theorem, which is sort of the controlling thing in the digital world of sampling theory. But if you want to go up to, say, around 70 megahertz, definitely reliable, you can use the Arduino Duo or the Zero. And that will then cover, even if you're active on 6 meter, if you want to build yourself a frequency counter there, or 4 meters. We have tried up to close to twice the clock frequency. That's around 96 megahertz. Then it starts to drop off in performance. It's simply not calculating or sampling the signal accurately enough. Now, the last decade or two, most rigs have had a resolution of 10 hertz, if not 1 hertz. And in the old days, in the HW12 days, people are probably pretty happy being, say, within 1 kilohertz. But now everybody sort of goes to the last zero and try to get it in place. The thing is, when you do this kind of tricks here, there's always an inaccuracy of plus minus 1 hertz. And there's nothing you could do about it, except sampling over a longer period of time and then sort of dividing afterwards. But that's the way nature works. So that's a frequency counter in itself. That's also one of the applications you can do in the Arduino itself, without GPS, without the SI chip. But if you want to take it sort of a bit further, there is the option about the GPS. I'll get back to that. But the Arduinos, and this is not just the Chinese clones, they use really, really, really cheap crystals, which are not even crystals, they are sort of ceramic resonators, and they are 0.5% or worse, and they're very sensitive to changes in temperature and so forth. So you will get some jitter on the readings. But one way you can improve it is that you can use the 1 PPS signal that comes out from a GPS every second. This is a fundamental schematic of a frequency counter, which is basically just here, that you have the signal. It can be a square wave, but it doesn't have to. And then the microcontroller samples it, and you present the result on the LCD or a USB or whatever use you have for it. But if you put in a GPS receiver in the circuit, you can use the 1 PPS as the gate signal, which means that every second there's a pulse coming out. And this is pretty accurate, even for these kind of cheap devices. So it samples the amount of pulses coming in 1 second. And then when you get the next one, you know, okay, I have started my counter. The next pulse that I get here, I'll stop my counter. This is pretty good, at least for standard radio amateur applications. You can buy the U blocks. Again, this is a clone for less than £10 from eBay. So for a relatively low amount of money, you can get yourself a decent frequency counter, at least for the HF and sort of lower VHF domain. So if we put it all together, this is the kind of mess you get. And this does not even show all the wires, because there is a problem with 5 volts. The cheap Arduinos, they run on 5 volts. But the SI chip is a 3.3 volts chip. Many of the boards, they have onboard level converters. So that may not be an issue. But to save cost, probably, the eBay GPS receivers, the U-blocks, don't have any level conversion. So you have to take that into account, meaning that you also have to buy a small level converter, which you can buy for less than £1, typically around $1.
But there is a very neat circuit that uses one FET and one resistor.
Yeah.
Each wire.
Yeah.
It's very clever.
And the thing is, when you go from 5 to 3 volts, you can just drop it in a Cena diode.
Well, it goes back. Yeah,
But the other way around.
both ways.
Yeah.
It's bidirectional.
Okay, I haven't seen that one, but
Probably what that thing's doing, though, Andy.
I think
no, this has 2. No, sorry, yeah, this is a 4-channel one. Yeah,
the SI actually looks as if it might have them.
yeah. Well, the thing on eBay or in China, if one figured out how to do it, the rest will follow, and
Yeah.
so that's some of the reasons why that
It's
these.
published on the Texas website.
Okay,
See how
yeah.
But that is awfully similar to the circuit you just described. You could
Yeah, but the thing is, this will cost you. I mean, again, around $1. Does it pay off to sort of build it yourself?
Yeah, that is doing it actually.
Yeah.
Yeah.
So the thing is that you have all these wires going around, and if you go back to one of the first slides that I showed you, it said don't mess around with the wires, because then the RF will mess around with you. So even though this is possible, and you can integrate all this and build it yourself or assemble it yourself, this will be less than £25. And then you have yourself a signal generator to beyond 200 megahertz. Fairly accurate. You can build yourself a frequency counter, a VFO if that's what you want. Then you probably need a knob somewhere. You can use one of those devices called a rotary encoder for doing it. Those can also be bought from eBay for less than £1. So it's really possible to find all these kind of, say, Lego bricks for radio amateurs in this. And it's a great way to get started, because then you can do sort of an immediately built, and the coding guys, they can start doing that. And then the RF guys can sort of sit in their part of the room and sort of design the RF way of implementing things. So, so that's very advisable. But you won't get any better performance than the one that Karen, the Russian amateur, had taken pictures of. But here's another way of doing it, and that's an implementation I've made with a group of friends. Here you can see that we have the GPS RF in one corner of the printed circuit. We have the RF over here separately with IQ outputs if that's relevant. There's an onboard low-pass filter that could be adapted. You have the crystal or crystal oscillator down here. We decided to go for an external oscillator instead of crystal. It gives better performance. The SI chip does have some wobbling when you change the registers or the loading values in it. If you switch it on and off, you'll see the trace coming. This is increasing frequency from you. You'll see kind of a J shape when you switch it on. And if you do that on and off, then it might become a problem depending upon your application. If it's a signal generator, it doesn't really matter that much, I guess. If it's a VFO, maybe, maybe not. You know better than I do for your own application. And then this circuit here, we have two power supplies or 2 voltage regulators. One for the digital domain, I think it's a 1 amp regulator, and then another one for the RF part, again to get the isolation. Then there are some other circuits on this one, because we see it as a more kind of RF platform for radio amateurs to learn how to write code and also get a good performance. There is a ULN 2803A, which is a Darlington driver array, 8-channel. So in case you have a series of relays for an attenuator, or you want to control some antennas for whatever reason, then you can at least drive each of them up to half an amp. That's one way of doing it. There's a USB port, so you can control it that way, and again program the code. And for the experimenter, you have a small wire down here, so you can put your alligator clip to it, so you don't have to connect that to one of the SMA sockets, for instance. Yeah, because sooner or later it will jump off onto the PCB, make a short circuit somewhere, and then you have to restart everything. And it's really cheap to do, and especially if you got the room for it. Then we also put a test LED. That's quite common on Arduino to have a test LED, but it's hardwired. Here, you just plug in a wire, and then you can sort of tap around the PCB to see, okay, the LED lights up the way it usually does. Of course, it can't give you an accurate reading whether it's 2.5 volts or 3.3, but it'll give you an idea, and you can see it if it's a pulsed signal, you can see that it flashes and so forth. Again, make it easy for the users. And it doesn't cost you a lot of money to put on an onboard LED for this kind of application.
Yeah. Sorry, but before we move on, there's a slot that looks like a riser, and I think it's labelled LCD. Is
Yeah,
an Arduino thing, is that for a display? Or
Yeah, you can attach a standard liquid crystal display here with a pair of 6 wires.
Okay.
And you have the onboard contrast control and backlight control and so forth as well.
But presumably you've got to write the code to write something to the display.
Yeah, but in the Arduino world, you just sort of load the display functionality, and then you say LCD write whatever you want to write. Hello world.
And it appears.
Yeah.
With the Arduino or the processor, is that of the
That's the processor here.
okay.
Yeah, and for this is the same processor as used in the Arduino Zero, the ARM processor, running at 48 megahertz. And then there's very deliberately an external EEPROM in a socket, so you don't have to be afraid of writing too many times to it. Just unplug it, plug in a new one, and again, they cost $50 or something like that. So all those kind of things, try to sort of think wide initially, and you can do it. This is half a Euro card size. Even after the Brexit, it will remain the same size. It has sort of some strange cutouts you can see, because it has been shaped to fit inside one of these German silver metal sheet boxes, if you're familiar with those. They're pretty good in the shielding stuff, or for shielding. So do it. Let's see how it performs. So you have Karen's pictures over here. Unfortunately, I don't have them for the very same frequency. But again, as I told you, increasing frequency, worse performance. Lower frequency, usually better performance. But the first one up there, that's a 10 megahertz, 10 meter or 28 megahertz signal in a 10 megahertz span. You have minus 50 dBc. And if you compare that between the two here, you got 10 megahertz signal and a 50 megahertz signal, and you can see there are a lot less spurious around. So it is possible, not by doing black magic, but sort of making a good design. And if we go to 244 megahertz, you can see the picture from Karen over to your left, and then there's a 200 megahertz equivalent here. So yes, it's possible to do it right. And the device, the SI chip, around $1.
700 dBc per hertz.
Mm. So it's possible to get a fair performance. The idea to doing this came from the next generation beacon platform that we are using in Denmark, what designed for us at 7IGY. Yes, it's rather costly, to be honest. But if you want sort of the Rolls-Royce performance, it's also in a different price league. This one is about a tenth of a cost, I believe. We don't know yet, but we'll see. So, just if you're looking for other devices that you would like to use, I've used the Piferino code. It's a generic beacon driver. But if you're looking for how to drive one of these devices, this is just a small commercial, then you can find on my homepage code for these ones. So you can also integrate those if you want to.
Do you do registers 2 programming on the LMX device?
Yeah. Well, Stinos a 2 Tango Golf did. He used one of your boards, I believe. I don't know. I think he did.
Very nasty little trap that.
Okay, might be. Usually I don't use them. I just get them fired up, and I see that they sort of work. I don't have anything else beyond 1 gigahertz for receiving
the
it.
LMX one,
Yeah.
If you reprogram the fractional register at the top, F register,
Yeah.
register 0, it does a VCO cal.
Okay.
So wideband glitches every time.
And then you get glitches, yeah. But he sort of took that into account. But the registers are more or less sort of carved out, so you just punch in the values in the code,
Yeah.
and you can play with them the way you want. So,
Usually for generating data modes, though.
yeah.
So
I'm not sure about when the presentations will be available. I think they will. That's my understanding. Anyhow, if you Google Arduino, the .cc is the right domain. Looks a bit odd though, but it's correct. RF0, that's where I have all the information about the PCB that I showed you, and also an online register calculator for the SI chip, down to millihertz precision. It's not running right now. We're still working on it. I hope during the Christmas holidays that we can sort of wrap things up. We still have to make a living next to doing all this kind of nice stuff. So, and then my own homepage, just for sort of various things, if you find that interesting. Jens, you did disappoint me. Not a lot of questions, not a lot of comments. A few in the first row, but that's quite typical. Please.
Si570 is very much more expensive.
Yes.
The only advantage seems to be it has onboard crystal.
Yeah.
How does this Si5351
Compare.
compare with that?
The question was, what's the difference between the Si570 and the and this chip here? There are many differences beyond price. You can't control the reference. That you can do in this one. You just take out one of the signals and route it back to the microcontroller, and then you can do that. That's not possible. There's only one output on the 50. The SI, the 570 is available, I believe, in 3 frequency intervals, if I'm not mistaken. It can go to 1.
Yeah, 3 qualities, very expensive.
Yes, they are.
Around 1490.
Yeah. So price range is very, very different, and unless you have to go sort of into the high UHF range, don't even think about it.
Fine.
Yeah. Use this one. It's so cheap. And if you burn it, buy another one. Buy 10. And I'm sure you won't get any problems at home anyway. So, yes?
Yeah, in terms of the level shifting issue,
Yeah.
it'd be worth mentioning the Arduino minis that are available in 3.3.
That's true. I deliberately did not sort of include the mini because, yes, it's available. Programming is a bit more tricky. You have to have another board and so forth. So spend that little extra. Yeah. Yes, it's true. Yeah, but it does run on 3.3 volts. It's only 8 megahertz, even though that's usually not a problem for most applications. Yes?
The Arduino clone that's being used on the Indian HF.
Which one did you say?
It's called Arduino.
Arduino.
Is that just a combination of those?
I don't know. It could be sort of instead of the RF0 kind of implementation, it might be more sort of tailored to radio. The RF0 is an RF implementation. It's not a radio implementation as such. It's also for learning and making something useful, designing it yourself rather than perhaps using it for a very tailored purpose. I don't know the Arduino itself as such. Yes? Okay. Thank you very much, gentlemen.
Thank you.